Hello, ladies and gentlemen. Welcome back. We're going to continue with Chapter 6 on probability and simulation, the study of randomness. We are going to do Day 1 of Chapter 6-2. All right, ladies and gentlemen, let's go ahead and get rolling here. So we've already talked about simulation. Let's go to this. So following along with what's in your book, ladies and gentlemen, page 408. Empirical. All right, the idea of probability is empirical. That is, it is based on observation rather than theorization. Probability describes what happens in very many trials. And we must actually observe many trials to pin down a probability. On page 409, randomness and probability. We call a phenomenon random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. Okay, so once you've done it many times, you start seeing a regular distribution. The probability of any outcome of a random phenomenon is the proportion of times the outcome would occur in a very long series of repetitions. That is, probability is long-term relative frequency. Okay, probability is long-term relative frequency. All right, on page 409, there's thinking about randomness. Now, I'm not going to read all of this for you. I would like you to go ahead and pause this video, open up your book, and read through what this is about thinking about randomness on page 409. Okay, especially the bullet points here. All right. So go ahead again, if you haven't done it already, pause the video and read through thinking about randomness on page 409. All right, I am going to continue with the rest of this lesson. So look at this little cartoon. Let's see what this one says. Mr. Wilson says most accidents happen within 5 miles of your home. Maybe we should move. You know, well, that's true, because think about it. Where are you most of the time? You're around home, right? You're going to stores here, there, okay, close to home. Well, the more frequently you do that, the higher your probability is of being in an accident. So yes, most accidents do happen close to home. All right, so probability models. The sample space S of a random phenomenon is the set of all possible outcomes. Okay, so that capital S is going to represent our sample space. We'll look at that when we look at this handout that I'm going to give you, or this next part. If we had a handout, if I was able to give it to you, what we would do. An event is any outcome of a set of outcomes of a random phenomenon. That is, an event is a subset of all sample space. Okay, an event is a subset of the sample space. So it's like an individual outcome. A probability model is a mathematical description of a random phenomenon consisting of two parts: a sample space, which we'll represent with a capital S, and a way of assigning probabilities to events. Okay, the multiplication principle, which we will see in a little bit when I go over that. Again, if we had a handout, I'd hand it out to you. The multiplication principle. If you can take one task, n sub 1, number of ways, and a second task, n sub 2, number of ways, then both tasks can be done in, you multiply them together, number of ways. All right, ladies and gentlemen, so we're going to look at a coin flip here to start with randomness. Now, this is what I was talking about as far as if I had a handout to give to you. Now, let me pull this in So if you have a printer at home, you certainly could print this. Again, I have this right above the video, okay, right here, randomness PDF. All right. Underneath this video, again, there's the College Board video that you could watch, Intro to Probability 4.3 daily video. All right. So there is a handout if you want to print it. Otherwise, you may have to pause to write a few things down. Okay. So again, write down what you think you need. Okay. You don't have to write every single word down, but there is quite a bit of stuff here for this one. So if you can print that, that might be a good idea. All right, ladies and gentlemen, let's get rolling here. So the idea of probability. The mathematics of probability begins with the observed fact that some phenomena are random. That is, the relative frequency of their outcomes seems to settle down to a fixed value in the long run. Consider tossing a single coin. The relative frequency of heads is quite erratic for 2, 5, or 10 tosses. But after several thousand tosses, it remains stable, changing very little over further thousands of tosses. All right, just to show you this, okay, there's an applet. Okay, you can see this the website up above if you wanna play with this on your own. So right now I've got it set so it's a fair coin. It's 50-50. Okay, so probability of heads is 50%, probability of tails is 50%. Now I'm gonna move this number of tosses down a little bit to 2 tosses. Okay, so 2 tosses is going to be very erratic. So if I toss it, okay, both times you'll notice, see this little blue line? I got heads both times. Okay, well, let me toss it 2 more times. Oh, wow. Okay, now it says I tossed it 3 heads out of 4. Okay, toss it 2 more times. Okay, now let me explain this here real quick. So right in the middle is 0.5. That's 50-50, right? 1 means that the first 2 tosses were both heads. So that means it started off with 1 because I didn't get a proportion. Down here is 0. So if we'd have started off with 0 heads, then it would have started down here. Okay, here's 2 more tosses. And 2 more tosses. And 2 more tosses. Okay, let me change this. Let me reset this. Okay, let me make this a little bit smaller here so it fits the screen a little bit better. There we go. All right, so let's increase this to 15 tosses. Okay, here we go. Watch it at the beginning and then watch what it does in the end. Wow, that was interesting. I haven't seen it do it that way before. Okay, there's 15 tosses. You will notice, ladies and gentlemen, in those 15 tosses, we got 10 heads and 15 tails. Okay, or not 15 tails, sorry. 10 heads out of 15 tosses. 5 out of 15 were tails. All right, let's just toss it 15 more times. Notice what it's approaching. Okay, so now I tossed it a total of 30 times. Okay, the more you toss it, the more you do it, the closer and closer it's going to get to the theoretical. Okay, so you'll notice it's starting to level off. Pretty cool. Okay, that is the idea of probability. Let me reset this and let me just jump that thing to, oh, let's go 100. Now again, at the beginning, it's going to be very sporadic. It's going to jump around all over the place. But then in the long run, it's going to settle down. Okay, here we go, 100 tosses. Isn't that cool? So 48 out of 100 were heads, 52 out of 100 were tails. Okay, it's leveling off at the theoretical. So if you can simulate something accurately and you do enough trials, it's going to get very, very close to that theoretical. Okay, now you'll notice it's going down a little bit, but now it's going back up again. All right, I think you got the idea. So with this, let me move that out of the way. So on this, I was just doing a little sketch. So that's 0.5, that's 0, that's 1. And again, you don't know where you're going to start. You might start at 0 because the first toss was not heads, or you might start at 1 where the first toss was heads. So, you know, if you toss a heads on the first one, it's going to start up here. And then it's just going to, you know, it's just going to level off. So that's the general idea that I want you to see there. If you do it in the long run, it settles down to a fixed value in the long run. All right, moving on. The language of probability. Random in statistics is not a synonym for haphazard, but a description of a kind of order that emerges only in the long run. We often encounter the unpredictable side of randomness in our everyday experience, but we rarely see enough repetitions of the same random phenomenon to observe the long-term regularity that probability describes. In the very long run, the proportion of tosses that gives a head is 0.5. This is the intuitive idea of probability. Probability 0.5 means occurs half the time in a very long number of trials. So we've got three people here. The French naturalist Count Buffon, he lived from 1707 to 1788. He tossed a coin 4,040 times. The result was 2,048 heads, or a proportion of 0.5069 for heads. Around 1900, the English statistician Carl Pearson heroically tossed a coin 24,000 times. Oof. Results 12,012 heads, a proportion of 0.5005. And then while imprisoned by Germans during World War II, the Australian mathematician John Kirk tossed a coin 10,000 times. Result 5,067 heads, proportion of heads 0.5067. All right, some terms. Random. We call a phenomenon random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. Probability. The probability of an outcome of a random phenomenon is the proportion of times the outcome would occur in a very long series of repetitions. Independent. Very important. One outcome of one trial must not influence the outcome of another trial, okay, or another. So they have to be independent. And random phenomenon. A random phenomenon has the outcomes that we cannot predict that nonetheless have a regular distribution in very many repetitions. All right, well, you all know about tossing some dice. Okay, let me see if I can pull in the dice. All right, there we go, ladies and gentlemen. I got the dice pulled in. So if you have some dice at home, you know, you could play with them if you want. So here I've got 4 dice. You know how they work, right? You roll the dice. It's all random. Okay, and so on. Let me move it back down to 2 dice. Okay, I'm sure you've all played some sort of board games or something with dice at some point in time, right? Okay, so we've got the idea of rolling the dice. And this is really cool. If I would click this output to a flip chart, it would actually record what is being rolled, but we're not going to do that, all right? So here we go. Waiting for doubles. Suppose you are playing Monopoly under a new rule where you must roll doubles to get out of jail. I don't think that's a new rule, is it? Take your first turn and roll a pair of dice. Did you roll doubles and get out of jail? If so, stop. If not, roll again. Did you roll doubles and get out of jail on your second turn? Okay, if so, stop. Okay, well, if we had time, ladies and gentlemen, we would perform this experiment. We would roll the dice. Everybody would do it independently, okay? And if we had a large class, this works pretty well, all right? So everybody would do it 20 times and we would record those results. But since we don't have that option right now. We're not going to do that. So we're just going to go down here and we're going to start looking at what the theoretical is. All right, suppose a red die and a green die are rolled at the same time. Fill in the chart below. All right, well, folks, what I'm going to do is I'm going to fill in with red and green. All right, so for example, if I roll the die, okay, the red one, okay, I could get a 1 here, a 2 here, a 3 here, a 4 here, a 5 here, a 6 here, right? Okay, and then the same thing could go right here, a 1, a 2, a 3, a 4, a 5, a 6, and then here a 1, 2, 3, 4, 5, 6, and so on. Okay, now the other die is green, right? So then I'll go like this. Whoops, hold on. That's not right. That's a 1. So I could roll a 1, 1, a 1, 2, a 1, 3, a 1, 4, a 1, 5, a 1, 6, and so on. All right? I think you get the idea. I'm just going to fill this in quick. All right, so these are all of the possible ways to roll the 2 dice. There we go. So how many are possible? Well, if you count that out, this is the counting principle, folks, okay? The counting principle or the multiplication principle. If you can do one task in a number of ways and a second task in a number of ways, then both can be done in an A times B number of ways. So there's 6 sides on one times 6 sides on the other, so there are 36 outcomes, right? Okay, so there are 36 outcomes. Now, the sample space. Now, when we write out, there's 36 of these, and we're not going to write all of these out, but I want to give you an idea of the notation you do for sample space. Okay, so capital S equals, you use a bracket. Okay, now, this is the whole sample space, 1, 1, 1, 2, 1, 3, okay, but we're not going to rewrite all of those. So what I'm going to do, just to show you, normally when you write out sample space, there isn't this many. But the sample space here is 1, 1, 1, 2, sorry, I'm not color coding here, 1, 3, 1, 4, I'm just going to go dot, 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 then I'm going to go 4, 6, nope, I'm going to go, let me back that up. I'm going to end it with the last 3, which is 6, 4, 6, 5, and 6, 6. Okay, so that's the notation you would use for sample space. All right, let's answer some questions. Oh, here is all of the different ones. All right, so if 2 doubles are rolled, what is the probability of getting each of the following events? All right, I'm going to take a moment, folks, and I'm going to copy over that table that I made, that chart, so that I don't have to flip back and forth. So I'll be right back. All right, ladies and gentlemen, I got it copied over. Isn't that cool? Just like that, boom, it's there. All right, so the first question is, what is the probability of doubles? Okay, let me do a little notation here with you. So what we really should do is we should put a P for probability and then the word doubles. Okay, the doubles, that is our event. Okay, that is our event. So the event goes in the parentheses. So, excuse me, doubles. If we look, the doubles are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay, well, there are 6 of them out of 36. Okay, or 1 out of 6. Always reduce. Always reduce. Leave it as a fraction unless otherwise stated. Okay, the next one is a sum of 7. So again, the notation really should be probability sum of 7. Okay, so I'm not going to write that for every single one, but that's the notation we should use. And again, that is an event. So the sum of 7, believe it or not, ladies and gentlemen, is the other diagonal. 6 plus 1, 5 plus 2, 4 plus 3, 3 plus 4, and so on. So again, that's 6 out of 36, or 1/6. Okay, the next one says the probability of a sum of 11. Well, 11, there's only 2 of them, 6, 5, and 5, 6. So 2 out of 36, which reduces to 1 out of 18. All right, now a sum of 7 or 11. Well, you can take, so or means to add in probability. I'm going to get ahead here of the notes and stuff, but that's okay. Or means to add, folks. So if I take the sum of 7, which is 6 out of 36, and I add the sum of 11, which is 2 out of 36, notice I'm adding the ones with like denominators. Okay, that is going to equal 8 out of 36. And let's see, 4 goes into both of those. So 4 goes into 8 2 times, and 4 goes into 36 9 times. So the probability of that is 2/9. 2 out of 9 times that should occur. Okay, either a 2 on 1 or both dice, or a sum of 2. Oh man. Okay, let's see here. We'll do this one in purple. So it has a 2 in it. Okay, so, well, this row all has a 2. This row all has a 2 in it. But make sure you don't count the 2 2 twice. Okay, don't count the 2 2 twice. And it says a sum of 2. Well, 1 plus 1 is 2. So let's see. If I count that, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 12 if I did that correctly. Okay, again, don't count the 2 2 twice. So 12 out of 36, and I believe that would be 1/3. All right. The next part, create a histogram of the sum of the 2 dice. All right, folks, so we're going to go ahead and make our X and Y axis. And if it's the sum of the 2 dice, well, the lowest sum is a sum of 2. Okay, and then 3, and then 4, and then 5, and then 6, 7, 8, 9, 10. Oh man, I'm not going to have enough room. Okay, you can finish it off. All right, now the frequency. Okay, I'm just going to do frequency here. I'm not going to do relative frequency. Remember, relative frequency is the percent or the decimal equivalent. Okay, I'm just going to do frequency, which is the count. So I'm just going to go 1, 2, 3, 4, 5, 6. Now I did not make this big enough. So if I look, how many add up to 2? Well, there's only one, ladies and gentlemen, that adds up to 2. Okay, so that means this would go up, over, down. Okay, how many add up to 3? Okay, well, there's a pattern to this, folks. There's 2 of them that add up to 3. So I'll go up to 2. Remember, histograms should touch. How many add up to 4? Well, that'll be 3 of them. How many add up to 5? Well, that'll be 4 of them. How many add up to 6? That'll be 5 of them. Oops, that's too far over. How many add up to 7? Well, that would be 6 of them. And then guess what, folks? It starts coming down again in the same pattern. So this histogram should be perfectly symmetric. All right, you can finish that off with 10, 11, and 12. All right. An experiment consists of flipping a coin and rolling a die. How many outcomes are there? Okay, again, that's the counting principle or the multiplication principle. So a coin has 2 sides and a die has 6 sides. Whoops, yep, sides. Hold on, that's supposed to be an S. Sides. Okay, so that means there would be 12 outcomes. Okay, what is the sample space? Well, the sample space would be heads, roll a 1, heads, roll a 2, and so on. Whoops, I don't want to put a comma between that one. And then tails. Okay, that is our sample space, all 12 of them. Create a tree diagram. Okay, remember how this works, ladies and gentlemen? So the coin, you might toss heads, you might toss tails. Okay, and then you're going to toss the die. Now you might get a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and so these are the possibilities. Sorry, it is not the neatest thing in the world. All right, so this is H1, this is H2, this is H3. I think I've got that on a slide coming up. All right, and so on. So that's what the tree diagram would look like. Yep, there it is. That's a lot nicer looking. It's on page 414 in your book. All right, so that's what that tree diagram looks like. Much, much nicer. There are different varieties of tree diagrams, and we're going to be looking at those at some point in this chapter. All right, not in this lesson. Let's keep going here. All right, sampling with or without replacement. All right, so for example, ladies and gentlemen, if I had, let's say I had a hat, forgive my drawing. Okay, that's a fair hat, I guess. Looks like a pilgrim's hat, I guess. All right, if I had a hat or a jar, and let's say inside that I have some green marbles, some blue marbles, and some red marbles. All right, so with replacement obviously means you're going to put the marble back. Okay, oops, let me make that a little bit smaller. So with replacement, so if I asked you what is the probability of drawing red, then draw green. Okay, now that this is with replacement. So, well, the probability of red is 2 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Okay, well, if I put the red marble back, I replace the red marble, then the probability of drawing green is going to be 5 out of 11. All right? So that's because you put the marble back. Okay? Without replacement, okay, I think you got the idea here, folks. Without replacement, same scenario, the probability of red, then draw and then the probability of green. Okay, well, the probability of red is 2 out of 11, but if you don't put it back, folks, the green would then be 5 out of 10 because you lost that one marble. So read carefully whether it's with replacement or without. Okay, so be careful. With replacement or without. Whoops, that's supposed to be, yeah, without replacement. Whew, I almost thought I goofed there. Okay, keep going. All right, probability rules. Memorize these, page 418. Memorize these. These are the 4. There's 5 of them, but we only are seeing 4 of them right now. Rule number 1, the probability of an event satisfies this. Remember, probability can only be a number from 0 to 1. You cannot have a negative probability, and you cannot have a probability bigger than 1. That's what that is saying. The probability of the sample space equals 1. Think about it. It's every single outcome. The probability of an outcome, it's going to happen. The probability is 1. If you add all of the probabilities together, okay, it's going to add up to 1. For example, if I go back and I add, ladies and gentlemen, okay, the probability of each of these events is 1/12. The probability of heads 1 is 1/12. The probability of heads tail is 1/12. Okay, there are 12 events there. If I add all of those 1/12ths together, it's going to be 1. So rule number 2 is the sample space, the probability model, the probability of the sample space adds up to 1, always. If it doesn't add up to 1, it's not a legitimate probability. Okay? Rule number 3, if we have disjoint events, also known as mutually exclusive, okay? If they're disjoint, mutually exclusive, they have no outcomes in common and so can never occur simultaneously. Okay, therefore, we can add those probabilities together. So if we have the probability of event A or the probability of event B, we can add those probabilities together. Now, when we get to rule 5, it's going to expand. Well, rule 3, there's more to rule 3. This is only part of rule 3. We will see the other part later, okay? So just remember, we're not done with rule 3 yet, okay? And that's the addition rule. Rule number 4, the complement of an event A is the event A does not occur, written as AC. So the complement rule states, so this is what it looks like. So for example, folks, okay, I'll get to this PowerPoint here in a minute. Okay, if I know the probability that it's going to rain outside is, let's say, 0.35, which is 35%. Okay, if I say, well, what's the complement of that? Okay, well, I could write rain complement, but that's the same thing as saying the probability that it will not rain. Okay, the complement is like the opposite of it. So what you're going to do is you're going to take 1 minus the probability that it is going to rain. Okay, so think about that. All right, and so then that would be 0.65, that it's not going to rain. The complement of rain is it's not going to rain. Okay, but oftentimes you're going to see that little C, that means complement. Okay, that is a notation you need to know. All right, let's keep going, ladies and gentlemen. It looked like it had stopped recording. I was a little paranoid. All right, so this, ladies and gentlemen, is showing disjoint events. Okay, this is kind of a strange looking Venn diagram. Not really a Venn diagram, but this whole rectangle is the sample space. And inside we've got 2 events. Okay, since they are not overlapping, okay, they are definitely mutually exclusive. Mutually exclusive events cannot happen at the same time. event A and event B. Sometimes, and this is going to get further, okay, not today, but further on. Well, no, I'll talk about it now. So if they do overlap a little bit, I'm going to expand on rule 3 here. So the probability of A or B, when they do overlap, they do share something, you're still going to take the probability of A plus the probability of B, but then you're going to subtract out the probability of A and B. Okay? So these are not totally mutually exclusive because part of A and part of B can happen at the same time. Okay, we'll expand on that in the future. All right, this is showing the probability of A and its complement. Okay, this is A complement. All right, probability of rolling a 5. Okay, there's some notation. All right, let me go back. I want to do that PowerPoint, so let me pull in the PowerPoint. I'm going to go ahead and pause this and get that set up. All right, ladies and gentlemen, so I got this from the instructor a couple years ago, and I really like this PowerPoint. All right, so we've got James Bond. All right, then we've got, it looks like back in the 60s where we've, got the flower in the hair and the peace sign on the cheek. All right, so let's go ahead and look at this. All right, so some guidelines. Guidelines for probability problems. With words or symbols, indicate the event of which you are finding the probability. Indicate what formula you are using and substitute information from the problem. Okay, you might want to pause and write these down. Substitute numbers for the quantities and perform the calculation. If asked for a judgmental based on probability, be sure to tie the conclusion to the computed probability. Okay, again, pause and write those down. A basic probability calculation. In Old Johnny's River song, Sweet Agent Man, the following line occurs. The odds are you won't live to see tomorrow. Okay, so go ahead and do a Google search, look up the song and listen to it. In a random sample of 1,000 of our special 00 agents over a period of 3 months, 993 of them did in fact see tomorrow. Presuming that the future will be like the past, what is the estimated probability of a randomly selected secret agent not seeing tomorrow? Well, okay, so here we go. This is our notation. Here's our sample space. The event seeing tomorrow. The probability of our sample, or sorry, they're letting S, that's not our sample space, folks. They're letting S equal the event seeing tomorrow. So the probability of that event is 993 out of 1,000. The complement of not seeing tomorrow is 1 minus that probability, or 0.007. Oh, wait, 0.007. Gee, isn't that funny? I really like that instructor. He has some funny stuff. All right, you get it? Haha. All right. Conditional probability. Okay, we haven't gotten to conditions yet, but we're going to go ahead and look at this one since it's in this slide. Okay, there's a lot with conditional probabilities we're going to need to talk about. Consider a song from the 1960s when flower power reigned supreme, at least in some circles. The following line appears in the Scott McKenzie song, San Francisco. Okay, if we were in class, I would play the song for you. You can look it up and play the song. Okay, if you're going to San Francisco, be sure to wear some flowers in your hair. Okay, I can't do it justice, but go listen to the song. All right. Consider a random sample of westbound drivers at a western location on US Route 66. 800 drivers are asked the following questions. Are you going to San Francisco? Are you planning to wear some flowers in your hair? Of the 376 drivers who said they were going to San Francisco, 128 indicated that they were planning to wear flowers in their hair. Of the remaining drivers, 85 indicated they were planning to wear flowers in their hair. Okay, almost done. What is the probability that a randomly selected driver traveling to San Francisco is planning to wear flowers in his or her hair? Okay, now this is a conditional probability. We haven't gotten to that yet. We're going to get to that in chapter 6.3, but I want you to look at the setup. So S is the event that the event going to San Francisco. W, the event planning to wear the flowers. Now this is conditional notation. Okay, so the first one is, what's the probability of planning to wear flowers and going to San Francisco? Well, that's 128 out of the 800. Divided by the probability that they're planning to wear flowers in their hair. That's the condition. Well, there's 376 out of the 800 that said they were planning on wearing flowers in their hair. So the numerator divided by the denominator, and really the 800s cancel each other out, I believe, you get 0.3404. All right, so that is a conditional probability. I probably will come back and visit this one when we get to it. All right, based on these data, there is evidence that going to San Francisco and wearing flower in your hair are independent events. Okay, are they? All right, yep, I'm definitely going to come back and visit this, folks, because we're going to need to talk about whether events are independent or not. So we see that the conditional probability was 0.3404. Okay, well, the probability of wearing flowers in your hair is 128 plus the 85 out of the 800, which is 0.2663. So, ladies and gentlemen, since they do not equal each other, it seems doubtful that going to San Francisco and planning to wear flowers in one's hair are independent. Okay, if that didn't make sense, don't worry about this quite yet. I'm going to go over this again in chapter 6.3. I think I'm going to come back to this problem in that video. All right, so can we conclude from this survey that Mr. McKenzie is responsible for increasing the amount of flowery hair? This survey was observational, not an experiment. Thus, Mr. McKenzie cannot be shown to be responsible for increasing the amount of flowery hair among those heading to San Francisco. You know, I think this guy would be really neat to take a class from, a class that would last more than just a couple of hours, because he has some really cool stuff. All right, moving on. I got 2 slides left for today. So page 421. Probability and a finite sample space. Again, assign a probability to each individual outcome. These probabilities must be numbered from between 0 and 1 and must have a sum of 1. Okay, that's rules number 1 and 2. The probability of an event is the sum of the probabilities of the outcomes making up events. All right, so I'm actually going to do a couple of problems from your book. Page 422, equally likely outcomes. Okay, let's take a look at that. But this is what I wanted to get to. So we have human blood here, type O, type A, type B. Now, you'll notice that AB is missing, ladies and gentlemen. So the first thing we're going to need to do is figure out, well, what's left. Okay, using our rules of probability, we're going to go ahead and add these 3 together and then subtract that from 1, and that's going to give us the type AB. All right, so let me go in here and let's make this a little bit smaller. And we're just going to go ahead and add the 0.49 plus 0.27 plus 0.20. All right, those add up to 0.96. Well, it should be obvious. That means the remaining amount that's left for type AB is 0.04. All right, so I've answered part A. Why? Because probabilities add up to 1, and that's what is remaining. Okay, B, Maria has type B blood. She can safely receive blood transfusions from people with type O and type B. What is the probability that a randomly chosen Black American can donate blood to Maria? Okay, so the probability of A, type A or B, okay, because she can receive both. Well, that would be 0.49 plus the 0.20. So the probability is going to be, what is that, 0.69? You just add those together. So that is the probability that a randomly chosen Black American can donate blood to Maria, because she can take type O or type B. All right, and I'm going to do 39 quick, and then we're going to end this video because we are already, wow, already up to 45 minutes. Government data assign a single cause of each death that occurs in the United States. The data shows that the probability is 0.45 that a randomly chosen death was due to cardiovascular, mainly heart disease, and 0.22 that it was due to cancer. What is the probability that the death was due to either cardiovascular disease or cancer? Okay, so there we're just going to go ahead and add those together for the first answer. Okay, and I believe that's going to be 0.67. Hopefully I did my math in my head correctly. And then what is the probability that the death was due to something else? Okay, so that would be the complement, right? The probability that it was due to the complement, not cardiovascular. Let's put H for heart disease. Okay, not heart disease or cancer. All right, well, that's the complement. 1 minus the 0.67, which would be the 0.33. All right, so you need to know how to recognize and use those different rules. We will be expanding on this in the next lesson. All right, folks, that was plenty long. I hope you made it to the end. We'll see you in class soon.